What are you holding now?
A six-pack.
A six-pack? Brilliant! What's it do?
Well, I figured out how to carry 6 beers at the same time.
Carry 6 beers at the same time? Brilliant! Let's drink them.
You know, I've been thinking, it might not be the smartest idea to drink 6 beers at the same time.
Don't drink 6 beers at the same time? Brilliant!
Brilliant!
Drink Guinness draft straight from the bottle and always enjoy it responsibly.
Wait a minute. Who is this guy and why is he in a Guinness commercial? The scientist you see in that iconic Guinness commercial is none other than William Seeley Gossett. He was eventually a master brewer at the Guinness Brewery, but in Guinness, when he was there as a statistician, he was doing research on how to make Guinness the best beer in the world. And he discovered that when you don't have a large sample size at very high N, you can't use confidence intervals about the normal distribution. It's a mathematical assumption needed for the central limit theorem. So he discovered a distribution that allowed you to continue to do inference about a population with smaller sample size. And that was considered such an important proprietary trade secret for the Guinness Brewery, he was unable to publish it. But William Seeley Gossett, not wanting to deny science his brilliance, he published it under the name student. And so this distribution became known as the student T distribution. And it's possibly one of the most important distributions in all of statistics because it allows us to compare 2 sample sizes. It allows us to reduce the sizes of the samples we need to draw inference. And it allows us to get significant traction when you have smaller data. So let's look at this a little bit further. You guys will recall the standard normal distribution. So this is usually represented by the letter Z, and we'll take a sample average, we'll subtract the reference mean, and we'll divide that by the standard deviation, which is going to be S divided by the square root of N, and this is in accordance with the central limit theorem. So this is what we use for typical inference when N is large. Well, what does the T distribution look like? The T statistic pretty much looks like the same thing. What's the difference? The reference distribution is slightly different. It's a little bit flatter and a little bit wider. So as we look at this, right, there's 3 lines here. I'll draw your attention to the T5 curve. This is for a sample size of 5, right? You can see that that's flatter than the tallest one, which is the standard normal distribution. As the size of N increases to 25 and you get this T25 curve, right, it gets closer to the standard normal. And indeed, as the sample size approaches infinity, the T distribution approaches the normal distribution. So for the T distribution, there's a single parameter. It is the degrees of freedom that is typically, for our purposes, N, which is the sample size minus 1, and it's free of other parameters. It's centered at 0. And otherwise, it's very similar in purpose to the standard normal distribution, except it meets the mathematical assumptions necessary for us to use it in smaller sample size. Let's turn our attention to an example problem. I'm going to do problem 33 on page 292 of DeVore's statistics textbook. So you'll see data along column A, and the nature of the data is probably not that relevant for our purpose. The first question asks to construct a box plot. So to construct a box plot, I'm going to highlight the data as you see here. I'm going to go up to Insert, and I'm going to look for a icon here where you can see that it looks like box and whisker plots, right? And so I can calculate the box plot right here. And then if I want to change the size, I can make it look a lot skinnier. And I can go and change the title if I wish to box plot, and you can of course label your data as you wish as well, right? So this is how we would create a box plot, and there's some other ways in which you can do that a little bit more efficiently. The next question is, does this look like it comes from a normal distribution? Well, I would draw your attention as we're looking at this, the mean and the median are about right, so it looks like it's a little bit symmetric. It looks like it's a little bit higher here on the higher side of the axis, so it might be slightly skewed a little bit compared to the whisker plot on the bottom. So I'm not quite sure, right? And then if I count the number of observations we have, right? Well, we come here to row 19, but we're not counting the first 2, so that tells me I have 17 data points. It's not exactly 30. Our rule of thumb would say that when n is 30 or more, I can probably just go straight to the standard normal distribution for my inference. So what I want to use for confidence interval is the t-distribution. Now, how do I go about constructing the t-distribution? Well, if we recall what that test statistic was, right? T equals x bar minus the reference mean over s times the square root of n, that results in a confidence interval that should be whatever our observation is, right? In this case, it was x bar. I'm just going to represent it like this. And that is plus or minus to indicate the interval. And that should be some t value times s divided by the square root of n. Okay, t over s times s over the square root of n. Well, how am I going to do that for a 95% confidence interval, right, about the mean? Well, the way we do this is the first thing we have to do is we have to calculate the average, right? So I'm going to use average, and I will highlight the data that I have, right, and that gives me an average. So that's the first part. I now need to calculate the interval. So the way we're going to calculate the interval is we're going to use t inverse, right? So t inverse. So this is going to convert the t distribution into a critical value you've seen in your book. Now, I don't believe in looking up critical values in the back of the book. I believe in using Excel, using our technology. So we're having to set that probability, right? So that probability, right, if we want a 95% confidence interval, right, let's look and see what happens when I put 0.05, right, and degrees of freedom, there are 17 data points here. 17 is n. So the degrees of freedom is n minus 1, so we're going to put 16. Now look what happens there. That gives me 2.11. What that's saying is, keep in mind, this is very similar to a standard normal distribution. So that's saying between 2.11 and negative 2.11 is 95% of the area under that t-distribution with degrees of freedom 16, which is, so for a sample size of 17 observations, right, this is telling me the width of under the t-distribution as a reference distribution. Well, that's not sufficient, right? We want to take this and we want to take the t-distribution, we want to multiply by the standard deviation of the data. So we're going to do that, standard deviation of the data. And I'm going to divide by the square root of n. So I'm going to put square root of n, and n is, in this case, 17. Okay? So that gives me my interval. So now, what do I do with the interval? Well, there is an upper limit of the interval, and the upper limit is going to be equal to the mean plus my interval width. And then my lower is going to be, lower limit is going to be equal to that mean minus the limit, right? And so I'm able to now construct a confidence interval on the true mean that goes between 430.5 and 446. Now there is another way that we can do this. If we go up here under the data tab and you go to your data analysis and we go to descriptive statistics, right? I can select my data, right, from 3 to row 19. It's in the columns. I can select an output range. I'm going to pick G4 here. I'm going to click Summary Statistics, and I'm going to say I want the confidence level for their mean at 95%. So when I run that, let's look at what we have. The mean that we have here of 438.29 matches the average we calculated on the data. Okay, and if we look at the minimum value of the data point, the smallest value is 418, the maximum value 465, right? And look at that confidence length, right? The confidence length of 7.786, right, is the same as what's been calculated right here. So what you can do is you can either use your data analysis toolkit here to quickly kind of get some of those descriptive statistics and run that, or you can actually calculate those yourself because you know the formula and you can code that in Excel. right? So that is problem 33 on page 292 of Devore's text. So I hope that every St. Patrick's Day you can think of the tea distribution and the contributions that Guinness made to the world of statistics. I'm Dr. McCullough and hope to see you soon.